Hello dear students, we will continue our discussion of Chapman's theory. We are looking to derive a unified expression for the rate of production with respect to height in an atmosphere which is decaying exponentially with respect to height. Okay. In the last lecture, we have obtained this expression for the production rate Q is written as C sigma n naught exponential minus h by h I infinity exponential minus sigma n naught capital H secant chi right. So, we know from the earlier discussion that Qm, the peak production rate Qm is C I infinity divided by E capital H cos chi, and hence C I infinity is equals to Qm E capital H secant chi. So, the motivation is now we are going to get an expression for production rate in terms of the peak production rate. Okay. So, Q is equals to sigma n naught exponential minus h by h Qm E capital H secant chi times exponential minus sigma n naught capital H secant chi exponential minus h by h. Right. So, we will rearrange these terms from the last lecture using, I will use the expression A. I have used this number or this label of equation number A for this factor of exponential Hm by capital H. Okay. So, Q is equals to, I will rearrange this expression, that is it. Q is equals to Qm sigma n naught capital H secant chi. Okay. Whatever that is appearing in the beginning, sigma n naught capital H secant chi. Qm is of course there. What else is remaining? We have exponential minus Hm by capital H times exponential minus sigma n naught capital H secant chi times exponential minus h by h. Right. Now, this is what we have. We can expand the exponential here. Okay, this one Hm by h. No, not Hm actually. I made a small writing mistake. So, this one can be written as only to the first order term. The first term is 1 minus h by capital H for this. Okay, let us say 1 and everything else remains the same. Okay, so now we can write Q is equals to Qm sigma n naught capital H secant chi into exponential 1 minus h by capital H minus sigma n naught capital H secant chi times exponential minus H by H. Okay, we'll take this expression ahead and write the production rate Q in terms of peak production rate and exponential Hm by capital H. This is using equation number A, which we have labeled in the last lecture. Okay, times exponential 1 minus small h by capital H. Again using equation number A minus exponential Hm by capital H multiplying exponential minus h by capital H. Okay. Again, simple algebra, Qm times exponential 1 plus Hm by h, this one. Okay. I'm writing within a single exponential minus small h by capital H minus exponential Hm minus h divided by capital H, or the rate of production is equals to Qm times 1 plus Hm minus h by capital H You can work out this simple algebra by yourself so that it is easy for you to follow. Okay. Qm times exponential, yeah, I missed. Yeah. Times exponential of all this. Let us say h minus hm divided by h as y. Okay, let us look back and try to see what we have done so far. We have just used these expressions into this and written the production rate in terms of peak production rate and all other variables. Adjusted or rearranged the terms in such a way that they appear in this particular form. Right. Now, what is the meaning of this expression? Only then we will be able to appreciate what it tells us. Okay. Q is the production rate, number of electrons produced per unit time. Qm is the maximum number of electrons that can be produced per unit time. Hm is the height at which maximum number of electrons are being produced per unit time. Small h is any height, capital H is the scale height. Right. Now, I am defining this length or this number as y. What is it? It is a referencing, let us say we have ionospheric profile like this, right? Now you have Hm here. The y-axis is the height and x-axis you call it as the electron density or the rate of production. It's one and the same, right? What it shows is that at a particular height, maximum number of electrons are produced. All right. So maximum number of electrons is the intercept that you can draw onto the x-axis. Now, what is this referencing that I'm telling you? I'm with a reference of Hm. So any height h minus Hm indicates how far is this point with respect to the peak production height. If it is a positive value, I am referring to those altitudes which are above the peak production height, and if it is a negative value, I am referring to those altitudes which are below the peak production height. Those values I am again normalizing in the units of capital H, which is a scale height. Now, the scale height is again temperature dependent. That's a different story. So, this is just a referencing with respect to the peak production height. So, I am calling it as Y. So, Y can be positive or negative. So, defining Y to be this, I can rewrite this expression as Q is equals to Qm times exponential of 1 minus Y minus exponential of minus Y. See, earlier we had the dependence of Q on, we have small h, we have hm, we have capital H, we have chi. What else? What else you have? What you have C. C is just a number, right? Now you have a simple expression in which everything else is embedded into the expression implicitly. So, this expression simply gives the production rate for any species which is distributed exponentially with respect to the height, okay, and for any angle, all right, okay. And this expression is in terms of a normalized quantity which is Y. It is sometimes very convenient to just express Q in the units of Q naught, okay. We have already defined what is Q, we have also defined what is Qm. Now, we define what is Q naught. What is Q naught? Q naught is the peak production rate or the production rate at chi is equals to 0. When is chi is equals to 0? With respect to the zenith. So, you define any angle as chi. Okay. Chi is equals to 90 means early morning or sunrise or sunset. Okay. So, when the sun is just above your head, so when chi is equals to 0 with respect to the normal incidence. So, we define Q is equals to Q naught. Qm is Q naught cos chi. Okay. So, with that we can rewrite the expression for Qm as C I infinity by E capital Hm. Of course, we know this already, right? So, cos chi, cos 0 becoming 1. So, this is going to be called as Q naught is equals to C I infinity divided by E Hm. You have a general expression for Qm, just modified that expression into Q naught. So, if this is Q naught, your Qm has to be obviously Q naught times cos chi, right? Of course, it is right there, okay, but I am just writing it as on purpose for you to understand. So, let us call it as A1. And similarly, from the previous lecture, we know that exponential of Hm by capital H is sigma n naught capital H secant chi. And for normal incidence, when chi is taken to be 0, we write exponential H naught by capital H is equals to sigma n naught capital H. I am just substituting the value of chi into this trigonometric functions, nothing else, which means exponential H naught by H is equals to all right, or exponential Hm by capital H is exponential okay. Let us say we call this as equation B. So using these two, using A1 and let us say B1 in where? In this, let us say we call it as D. In D, we can write okay. So using these two into this expression, we can write, I am just writing the final expression, Q is equals to Qm exponential of exponential H minus Hm by capital H times e to the power of exponential of exponential H minus Hm by capital H, or Q is equals to Q naught cos chi times secant chi times exponential 1 plus H naught minus H divided by capital H minus secant chi exponential okay. Now let us call Z is equals to H minus H naught by capital H. This is also a referencing with respect to the height of peak production in normal incidence, which is called as H naught. So now we can write this as Q is equals to Q naught exponential 1 minus Z minus secant chi times exponential minus Z. We have earlier form of production rate as Q is equals to Qm exponential 1 minus Y minus exponential of minus 5. Okay. We have two equations. The first one is for chi is equals to 0, and this one for chi can be any angle. Okay. Now, we will stop it here. We will discuss the consequences of this mathematical treatment and try to relate the inferences of these mathematical equations directly into the understanding of ionospheric layers, or the D, E, F1 and F2 layers. Okay.